There, now I'm recording. Thank you for those that are attending live, and welcome to those that may be watching an archive version at some point in time. I'm Matt Helmers at Iowa State University and the director of the Iowa Nutrient Research Center. And it is my distinct pleasure to introduce Dr. Antonio Arenas from the University of Iowa, IIHR Hydroscience and Engineering and Iowa Flood Center to talk about some of the work that they've been doing on looking at Des Moines River upstream mitigation. And so those on here probably know the Iowa Nutrient Research Center is housed at Iowa State University, but is a Regents center and represents University of Iowa, Iowa State University, and the University of Northern Iowa. So it's great to have one of our colleagues from the University of Iowa on here to talk. And so I'll turn it over to Dr. Arenas.
Thank you, Matt. I really appreciate the invitation and the kind introduction. So, you know, thank you for everyone who is in attendance. Hopefully it's going to be an interesting presentation. So my plan for today is to talk about the Des Moines River upstream mitigation study. But before I go on, I want to acknowledge my collaborators. So I work on this project with Professor Larry Weber, Dr. Nate Youngs. I also work from the University of Iowa as well. Dan Gills and Mike Krasowski, one of our students, at least a student at that time, helped here. Funding for this project came directly from the city of Des Moines, more specifically from the Public Works Department. And we work with Jonathan Gano and Dan Pritchard at that Public Works Department of the city of Des Moines. Before I go on and talk about the details of this project, I always kind of want, I think I should start any talk about flooding in Iowa with this map, or a map like this that allows us to, you know, get, I guess, the big picture of how intense and how much of an environmental challenge flooding is for the state of Iowa. When a catastrophic event happens, the President of the United States has the authority to issue a presidential disaster declaration. And that process activates quite a few programs and provides assistance dollars for those communities impacted by that catastrophic event. Catastrophic event can be an earthquake, a wildfire, hurricanes, tropical storm, a pandemic, and flood events as well. The agency that keeps track of all those events and all those presidential disaster declarations is FEMA. And they do a good job about keeping records, and those records are open to the public. And I went to their database and searched for how many times counties in Iowa received or were named in disaster declarations just in relation to flood events. And I created this map with data from, as you can see there, from 1989 to 2019. And you can see that the state of Iowa, if you make the analysis on a per county basis, you see that the total number of flood-related disaster declarations has been a little bit over 1,000. Maybe another take-home message from this map is that no county has escaped, you know, catastrophic events severe enough to receive a presidential disaster declaration because of flooding, because you see that the count starts at 4. So the county in this map that has received the fewest presidential disaster declarations because of flooding has received 4. So that's just an illustration of how intense, you know, flooding is for the state of Iowa. And this is by no means a comprehensive list of the flood events that have happened in this time window, because this only, as I said before, includes the big events, if you want, that rose to the level of a presidential disaster declaration. So that's what flooding is for the state of Iowa. Now, about the Des Moines River upstream mitigation study. What I'm going to be talking about today is analysis that we made in the Des Moines River upstream from the city of Des Moines. So think about 6,300 square miles upstream from the city of Des Moines all the way up to Minnesota. We use hydrologic model to evaluate the flood reduction benefits that can be expected from different structural and nature-based mitigation strategies. And to make those analyses, we use a model that was developed in-house by my colleagues at the University of Iowa. And that model is called GHOST. GHOST stands for Generic Hydrologic Overland Subsurface Toolkit. And it was developed mainly by my coworker, Dr. Marcela Politano at the University of Iowa. I don't know how familiar you guys are with hydrologic models, but a hydrologic model is at the most fundamental level, no different from one of those setups that allow you to kind of estimate how much of the rain is infiltrated and how much of the rain moves downstream as runoff, rainfall simulators I'm talking about. However, of course, it's not something that we have physical, but that we do have in our computers. What a hydrologic model, or what this hydrologic model does, is goes ahead and partitions the area, in this case, the Des Moines River watershed upstream from the city of Des Moines, into different computational elements. And I don't know if you can see the triangles there for the Boone watershed, and basically partitions precipitation into the different components of the hydrologic cycle at each one of those triangles or computational elements, and then aggregates the response at each one of those triangles to make a prediction about what happens at the watershed scale. So in kind of in simple words, we do provide rain, we do provide other climatic data, and then the model makes predictions about flows at different places throughout the watershed. This type of model is classified or typically referred to as process-based or physically based hydrologic modeling. Is known for being computationally intensive, so it does require most likely some sort of parallel computer. And in addition to that, they are known for being data hungry. So they do require quite a bit of data to be parameterized. That's on the I guess negative side, but on the plus side, as you will see later on, the level of achievement or the level of a model performance that you can get using this process-based hydrologic model is, in my opinion, the most advanced model performance or hydrologic model performance that you can achieve. As far as forcing data or precipitation and climate data, we used information from a database maintained by NASA and other federal agencies called NLDAS that provides hourly precipitation and climate data with a spatial resolution of about 10 kilometers. So each one of those red dots in the right-hand side map, in the right-hand side figure, has one data point every hour, for precipitation, temperature, relative humidity, and all the variables needed to calculate evapotranspiration. So we do use that information at each one of those red points, apply that data, and then let the model make predictions, and basically at any point that we want. That is as far as the forcing data, and maybe just to give you an idea, we have applied this modeling that I'm talking about today at the Des Moines River watershed, of course, which is the title of my presentation, but there are other watersheds that we have been analyzing using this model. And in particular, I'm talking about the eastern watersheds that are participating in the Iowa Watershed Approach project, as you can see there. So the Des Moines River watershed, one relatively small watershed in the Great Lakes region. We have also applied this model into the Upper Iowa River watershed, the Upper Wapsipinicon River, the Middle Cedar watershed, and Clear Creek as well. But coming back to the model, maybe if I can make a historic note. So if you look at the scientific literature, the first time that what I would call the blueprint for this type of hydrologic model appeared in the scientific literature, it's late 1960s or early 1970s. However, that kind of remained being just a blueprint, and no one kind of actually implemented this type of modeling mainly because of two reasons. Because computing resources are needed, as I already said, and also because at that time there was no readily available information about land use, soil types, geology, and certainly not spatially distributed precipitation data that, of course, we can find now relatively easily. And here I want to give you an idea about the model performance, but I'm showing model results. So we made analysis for 17 years, starting in January 1st, 2002, and ending all our simulations in December 31st, 2018. So that's 17 years of continuously simulated hydrology. And I just want to emphasize that. So there's a big difference in trying to achieve good model performance over a very, very long period of time and just use modeling techniques, hydrologic modeling techniques to analyze, a couple of weeks, or what we call event-based or episodic simulation. So this is a long-term simulation, which is, in my opinion, a very high hydrologic bar, because you want to come up with model parameters that allow you to make predictions over 17 years with drought periods, flood periods, snowmelt periods, and everything in between. And I'm just giving you an idea about the model performance, how the model predictions compare against observations at 4 different points throughout the watershed. As you can see, the A, B, C, D locations are down here. So the Des Moines River at Humboldt, the S4 Des Moines at Dakota City, Boone River near Webster City, and the Des Moines River near Stratford, which is, I believe, the downstream most USGS station that is unaffected by backwater effects from Saylorville. And you can see that there is a very good agreement between the red dots and the blue line, the red dots being the observation taken at the USGS station at each one of those locations, and the blue line being the model prediction. So, and as I always say when I'm presenting this type of a slide, so the dream would be to have the blue line perfectly coinciding with the red dot. That would be a model, a perfect model, but at the same time, that's a model that does not exist, because by definition, a model is a simplification of the reality. So that's kind of an unattainable goal, but we always try to get a little bit closer. So, and I can tell you, even though I'm not showing results for later in the analyzed time window for 2018 or anything like that, I can tell you that this level of model performance was maintained throughout the entire window that we simulated. We calculated the commonly used metrics to evaluate model performance, and all of them came out very good. So another idea about model performance, what I'm presenting here is just monthly runoff depth. So if you take the volume that was observed or predicted by the model, of course we have both, you take that volume and you divide that volume by the drainage area, you get units of length or runoff depth. And I'm presenting how model predictions compared against observations for all the months of the year during the 17 years, and for the 4 places that I showed before. And as you can see, there is a very good agreement between the monthly runoff and predicted and observed. And the last slide that I have about model performance here is the annual peaks. So I extracted for each one of the simulated 17 years, I do have information about the observation, and I do have information about the model prediction. And I extracted simply the annual peak at each one of those locations. And once again here, if the model were perfect, you will have all those red dots perfectly coinciding with the black line. And that would be a model that predicted perfectly each one of the 17 annual peaks within the analyzed time window. But you see the trend is there. So we feel very good about the model performance here that we were able to obtain for this Des Moines River watershed. This model has also a tile drainage module that based upon the location of the predicted water table. So this is a surface subsurface model. So the model is not only making predictions about stream flows, but also a fluctuating water table at each one of those computational elements, at each one of those triangles. And based on the location of that predicted water table, the model makes a prediction about tile drainage flow, so tile drainage contributions to stream flow. And I'm just presenting here an example of predicted runoff with the red line, the predicted average water table for the entire domain, and also the predicted contribution of tile flow based on the model results to that stream flow. And you see how the model is, the predicted tile drainage flow is highly dependent upon the location of the predicted water table, because that's how we set up the model. And as the water table goes up, so does the predicted tile drainage flow. And as the water table goes down, there is a decrease as well in the predicted tile drainage flow. So maybe some interesting point that I want to say is that at some point during early September or late August, you see that at least based on the model predictions, almost 100% of the flow that we see in the Des Moines River watershed is coming from tile. At least that's what the model is predicting here. On the right-hand side, I have a panel, a bar diagram that shows the predicted, this is of course everything based on model predictions here, how much of the annual flow is associated to tile drainage flows. And you see that there is quite a bit of variability according to the model predictions. But you see a clear pattern that for very dry years, like 2012, for instance, the contribution of the predicted contribution of tile drainage flows to stream flows in the Des Moines River watershed goes up to a little bit over 80%. Whereas during very wet years like 2010 or 2008, that contribution of tile drainage flows to stream flow goes significantly down to a little bit over 20 or 22% on an annual basis. On average, you see that based on these results, you can say that around 30–35% of the annual flow comes from tile. That is at least between 2002 and 2018. So we have all that, and as I said before, so once we made certain that the model was a very good representation of the hydrologic conditions in the Des Moines River watershed using the window between 2002 and 2018, we used the model to evaluate different flood mitigation strategies, structural and nature-based. And specifically, I'm talking about we simulated, we modified the parameters of the calibrated model to simulate different levels of implementation of native vegetation. We also ran a simulation that tried to mimic what would happen if every single row crop in the watershed adopted cover crops and no-till practices. We also came up with a system of distributed storage, so ponds, about 1,200 ponds located throughout the study area. And we ran those simulations using both historic precipitation, so what actually happened, at least based on the climate database that we use, what actually happened between 2002 and 2018. But we also ran a simulation, a very simple simulation that we came up with to try to account for the projected changes in heavy precipitation throughout, basically throughout the Midwest. So it would be a kind of a simple way for us to start talking about how things are going to be based on the projections of heavy precipitation, increases in heavy precipitation due to climate change. So, and that's what I'm going to be talking about from here on. Maybe some words about the system of distributed storage that we came up with. So we did use the agricultural conservation planning framework, so the ACPF tool, in about 68 HOP 12 throughout the watershed. So not in all the, I think it's 186, so close to 190 HOP 12s in the study area. So we did not run the ACPF tool for each one of those HOP 12s, but we completed in 68. And that gave us an idea about the potential locations that are suitable for construction of detention structures, so wetlands and ponds. And we came up with a system that, as I said before, has between 1,200 and 1,300 ponds. And each one of those ponds provides about 20 acre-feet of flood storage. And we place them strategically throughout the watershed. And that's basically what I'm trying to represent there. So each one of the dots in this map does not represent an individual pond, but just more like an aggregation of ponds that are located upstream from that particular point. And I have information about how much acre-feet of storage was simulated upstream from each one of those 8 index points that you can see on the left-hand side. For the native vegetation scenario, we rely heavily upon data generated during Strips project, which this is a project that I am personally a very big fan of. I think it's a very clever and very nice strategy, not only for achieving water quality results, but for achieving flood reduction benefits as well. So we relied on publication and published data from this project, and we came up with a set of parameters that can represent the conditions that we should expect if we go ahead and replace row crop agriculture with native vegetation. And here I have a summary of all the scenarios with a little bit of a description about what they are about. And some of the figure numbers are actually more related to a final report that we produced for this particular project. So I think the labeling of the scenarios is kind of self-explanatory, but I'm going to go real quick over some of them. So the MV 100% scenario assumes that every single current row crop acre is replaced with native vegetation. MV 20% assumes that only 20% of the existing row crop acres are actually replaced with native vegetation. CC 100% assumes that every single row crop acre adopts cover crops and no-till practices. The ponds, basically the distributed storage system that I explained before, and then there are two hybrid scenarios that assume that the native vegetation is implemented or replaces, I guess, 20% of the current row crop acres, and the 80% of the remaining row crop acres adopt cover crops. And the same applies for the last scenario, but only that you add the ponds on top of the MV 20% and on top of the CC 80%. So those are the scenarios that I'm going to be talking about. And the goal of this project was to try to quantify the flood reduction benefits. And I took these two images from the latest climate science special report. So the one on the left-hand side shows some analysis, and that is a fairly extensive and comprehensive report put together by NASA, the National Weather Service, and a bunch of federal agencies and universities. And it is, in my opinion, I guess, that the latest information kind of approved by the scientific community working for the federal government. That's one way that I used to describe it. So they did analyze past data, and they found out, I'm talking about the image on the left-hand side, and they found out that in the period between 1958 and 2016, the heavy precipitation data, so as you see in the title of that image, is the 99th percentile. So just the heavy downpours, they did increase by about 42% in this in the Midwest. So that's with the past data. And the maps on the right-hand side showed their projection about how heavy precipitation is likely to change for the mid and late part of the current century and under different emission scenarios. So for instance, if you read the map on the right bottom, you see that there is a plus 20% around Iowa and the Midwest. And what they are telling us is that based on their predictions, under high emission scenarios and for the late part of the current century, the 21st century, the 20-year return period precipitation, so once again, kind of heavy downpours, are likely to increase by 20%. And we try to mimic that in a very simple way, and I will talk about that a little bit more later, how we implemented that in our model. So I'm presenting here the first set of comparisons. So all the triangles for the 8 panels that I'm presenting here represent the baseline conditions, or in other words, how the calibrated model captured the reality. And each one of those symbols, both the triangles and the red dots, represent an annual peak. So you have in each one of the panels, you have 17 triangles, 17 annual peaks between 2002 and 2018. And you also have 17 red dots. And those are, again, the annual peaks predicted by the model, but not with the current land use, but with the assumption that every single existing row crop acre in the Des Moines River watershed was replaced with native vegetation. And you have 8 panels because we kind of put together the story around the 8 index points that you can see on the left-hand side. But this is a spatially explicit model, so we could extract information basically anywhere in the watershed. But at some point, you have to, of course, write a report and tell a story, and those were the 8 points that we chose. So, and I have another, in the following slide, you will see a little bit more, not that many, 8 panels, but just 3. And I will use those to tell the story, but hopefully it's clear. So each one of the symbols, an annual peak, the triangles represent baseline conditions. So what happened with the current land use and with the current forcing data that we use, so precipitation and temperature and stuff like that. For each one of the 8 places that you can see there. Massive, massive, massive reductions in annual peak floods coming from, unsurprisingly, by the way, coming from replacing the existing row crop agriculture with 100% of the existing row crop agriculture with 100% of native vegetation. And I have here maybe an image that I'm gonna use to explain a little bit better. Hopefully by this point it's kind of clear. But I'm again showing, not for the 8 points, but I'm showing here results for the same location. So which is the Boone River at Webster City. Once again, the triangles represent the baseline conditions. And by the way, since it is the same location, the triangles represent the same values in each one of the 3 panels. So baseline conditions, the calibrated model. And the red dots represent each one of the scenarios that is kind of stated on top of the panel. So you have the annual peak floods predicted by the model by replacing 100% of the row crop acres with native vegetation, just by replacing 20%, and just and by assuming that every single current row crop acre adopts cover crops and no-till practices. And I'm also kind of reporting the average peak flow reduction there. So almost 56% for the NV 100%, almost 15% of the NV 20%, and cover crops 18%. And there is there is a lot to be said about these plots. Some of the things that I found more interesting, it is that the earlier the peaks, the actual peaks, the observed peaks, or actually the peaks that were captured by the calibrated model happen in the year, they were more susceptible to be reduced by these nature-based flood mitigation strategies. In other words, if we are talking about a peak that actually happened, let's say in late April, May, even early June, that particular peak was very likely to be highly reduced by this implementation of native vegetation, different percentages of native vegetation of cover crops. And conversely, if that particular peak happened later in the fall, let's say September or even October, the reduction was not as significant. And that is because, at least the explanation that we came up with, that is because for that time of the year, late September and October, the state of Iowa has a very good flood protection system in place, and that system is called corn and soybeans, right? So we have vegetative cover throughout the state. We do have relatively dry soils because the plants have been taking water from the soil via transpiration. So those peaks are not as susceptible as to be reduced. And you also see that there, at least based on the numbers that we are coming up with, there is almost an equivalent, if you want, or they are very comparable, the reductions that we can expect from the NV 20% and the full adoption of cover crops throughout the watershed, with the cover crops performing a little bit better. However, I think, and I will elaborate on that at the end, I do think that I'm being a tiny bit unfair with the cover crops, but I will talk about later on about that. So hopefully this is clear. I'm going to move on. And this is the summary of the flood reductions estimated for each one of the scenarios and at the 8 index points. So kind of a messy plot, but hopefully by this point is somewhat clear. Black bars represent the native vegetation 100%. So, and you see that based on the model results, basically 50% of flood reduction, peak flow reduction can be expected from moving every single row crop acre back to native vegetation 100%. And this topic is, this is not the first time that I present this type of analysis. And I've noticed that, and for obvious reasons, that when I start talking about replacing 100% of the current row crop acres with native vegetation, that is a topic that perhaps is not appreciated by everyone in the audience. But I always clarify that that is not something that we at the Iowa Flood Center are advocating for. What we believe, or at least what I believe, is that this type of analysis is important because it allows us to gauge what is the maximum flood reduction benefit that can be expected from flood mitigation strategies in general. So I guess I'm making the case that the MV 100% represents the best you can do as far as flood reduction. So meaning that floods will not be eliminated. So floods are a fact of nature, and we have always lived with that. But at least that is a measure of what's the maximum theoretical possible that can be achieved as far as flood reduction. You see that the, like I said before, the MV 20% and the cover crop 100% achieve comparable peak flood reductions, at least based on the on this results, and that the hybrid scenarios provide about half of the flood reduction that can be expected from the native vegetation 100%. So, and here I have this slide that uses basically the results from the MV 100% scenario to measure or to gauge. I use this as a yardstick, if you want, to measure how much can be achieved, how much of the results of the flood reduction benefits that came from the MV 100%, how much of those benefits as far as flood reduction can be achieved using NV 20% or can be achieved using full implementation of cover crops or ponds or the other scenarios. And this, if you see, for instance, cover crops, full adoption of cover crops kind of provide about 30% of the flood reduction on average that the native that the MV 100% scenario provides. And for the hybrid scenarios, as I said before, you see that those two scenarios provide about half of the flood reduction that is predicted by the model using the MV 100% scenario. So this is as far as the comparison of the scenarios, and hopefully it's clear, but all that I've said up to now was estimated using historic precipitation. So I haven't altered the precipitation yet. So, and I have results later on for that. But this is based on how that database that I mentioned at the beginning, so the NLDAS database, captured the climate of this region in the window between 2002 and 2018. This is using historic precipitation as well. And what I'm presenting here is the following. So between 2002 and 2018, the emergency spillway of Taylorville was activated twice. Once in 2008 and another time in 2010. So I used the model results to investigate if all the scenarios that we simulated would have been able to prevent the activation of the emergency spillway. And for that, I tried to estimate not annual peak flow reduction, but volume reduction. So from the Taylorville's perspective, in my opinion, the volume is what matters most than certainly more than the annual peak. For perhaps small communities distributed throughout the watershed in the upstream from Taylorville, I would argue that what matters most is the actual annual peak, because that's what can affect them. Taylorville is more, I mean, I guess the operation of the Taylorville reservoir is more affected by volume as opposed to just annual peak. But coming back to the story here, so 2 times between 2002 and 2018, the emergency spillway was activated, 2008 and 2010, and I used observations to estimate how much volume actually passed over the spillway. And that is what is presented in the table there as ES, emergency spillway. So in 2002, almost 350,000 acre feet of water moved towards the city of Des Moines, passing over the emergency spillway, whereas in 2010, a little bit over 100,000 acre feet of water moved over the emergency spillway, which is obviously something that is undesirable. So the ideal operation of the spillway will prevent that at all costs. So the ideal case is to have always controlled discharges passing downstream from the reservoir, as opposed to uncontrolled discharges. That is what the emergency spillway does. And I estimated the volume reduction using all the results that I presented before, the volume reduction, selecting an integration window of 30 days prior the activation of the emergency spillway. So since I have hydrographs, of course, if I make the integral of a hydrograph over a certain time window, that gives you a volume. And I estimated the volume reduction expected from each one of the scenarios that I already talked about by simply calculating, by simply integrating the hydrographs over a window of 30 days. So, and you see that for the year 2008, the only scenario based on my results that could have prevented the activation of the emergency spillway was the MV 100%. So that is a confirmation of how extreme, if you want, the 2008 year was as far as precipitation and volumes. So only the MV 100% generated a volume reduction comparable to the volume of water that actually passed over the emergency spillway. However, for 2010, the story is different. So we do see that for the almost 100,000 or just a little bit over 100,000 acres of water that actually passed, based on observations that actually passed over the spillway, the Saylorville emergency spillway, you see that we have a greater reduction based on the NV 100%, but we have a fairly comparable reduction for the NV 20%. I would argue that the CC 100% scenario would have knocked down that volume of water moving over the spillway in an appreciable way. And all the both hybrid scenarios, the MV 20%, CC 80%, and the one with the ponds, would have, based on my analysis, prevented entirely the activation of the emergency spillway in 2010. And here there is an interesting point. So you might remember that I said before that as far as annual peak flow reduction, the MV 20% and the cover crops were somewhat comparable, with the cover crops perhaps performing a tiny bit better peak flow reduction. However, when it comes to volume reduction, at least based on these integrals that I'm presenting here, the MV 20%, the MV 20% does clearly better as far as volume reduction than the cover crops 100%. So one of the conclusions here is that perhaps once again, from the standpoint of communities throughout the watershed, it appears to be a little bit more convenient flood mitigation strategy to emphasize the cover crops. However, for the operation of Taylorville, it appears that the MV 20% and the associated greater volume reduction appears to be a little bit more advantageous. So that is that as far as Taylorville, and this is the end of my analysis with historic precipitation. And this is the second to last slide that I have here. And I'm presenting here, I've struggled quite a bit about how to best present these results, and we landed on this plot, but I'm still kind of figuring out how to best present this. So I'm presenting here results from what I call the increased precipitation scenario. And you might remember that I presented those maps from the climate science report that were projecting that for the late part of the 21st century and under high emission conditions, they are projecting that the heavy downpours are going to deliver more water, 20% more water. So, and we really wanted to come up with a way to represent that. And we did the following. So at the beginning of my presentation, you might remember that I talk about all those red dots for which we have hourly information about precipitation and other variables. So we decided to alter that precipitation, the precipitation that actually happened between 2002 and 2018 in this manner. So we search for each one of those pixels we searched the top 5% rainiest days. So we did not alter every single precipitation data set or data record that we had for the pixels that we used to force the model. We only alter, once again, the heavy precipitation days, the top 5%. And what we did for that, for those particular days, we increased the volume of precipitation by 20%. So it's a very simple way to try to mimic what they are projecting that is going to happen under high emission scenarios in the later part of the current century. So we increased the heavy downpours in the year 2002, between 2002 and 2018, and then we reran the whole thing. So we reran 17 years of altered precipitation, keeping all the other variables unmodified. And then those results were used to generate the plot that you guys are looking at. So maybe let me try to explain what you are looking at. So now we have, again, simulations with increased precipitation. So we increase the amount of water that came in the heavy downpours by 20%. And then I'm comparing the average peak flow reduction against what the model predicted for the baseline conditions using historic precipitation. So, and that's why you see these negative reductions. That's something that I'm still struggling to how to communicate better. But let me see if I can do a better job. So the blue bars are presenting for each one of the index points. The blue bars are presenting a negative reduction. And that is obvious because the blue bar is comparing the peak flow reductions by taking the values of the calibrated model with historic precipitation and the same calibrated model but using increased precipitation. Of course, if you don't put in place any flood mitigation strategy, the peaks are not going to be reduced, they're going to increase, and that explains why the baseline has negative values, so negative reduction, which is of course an increase in the peaks if you don't do anything at all. And precipitation increases in the way that I described before. And you have the same information for all the other scenarios. On the other end of the spectrum, you see the black bars. You might remember from my previous slide that I had the black bars providing reductions in the 50% kind of level. So right now, when you account for the increased precipitation, those reductions do not get to the 50% level, and they are lower to the around 30% level. And you can see, for instance, that the hybrid scenario that is called here MV 20%, CC 80% provides basically zero reduction. So you see kind of tiny values, zero reduction, which means that the MV 20%, CC 80% scenario is going to just be able to counterbalance the increase in heavy precipitation, or in other words, the future floods are going to be the same with that scenario in place, are going to be the same as the floods observed on average, at least between 2002 and 2018. So of course, the take-home message here is that if we believe in all the assumptions and the model is giving us an idea about what can happen with that 20% increase in heavy downpours, so a lot of work needs to be done, I guess, to make a more resilient watershed throughout the state. So that is that. And this is my future work. This is my last slide. Hopefully I'm doing fine with time. What else can be done? So how can we make this analysis better? So there are many ways. So, and I try to summarize here 3 different aspects that our team and I personally would like to move my research towards. So the first one is the concept of storm transposition. The National Weather Service began collecting radar-based precipitation data in 2002. So at this point today, we do have about, roughly speaking, about 2 years of, 2 decades, I'm sorry, 2 decades of radar-based hourly precipitation data. So we have a collection of storms that we can use to make storm transposition. And that is kind of a fancy way of saying, but so what if, so we have heard all the story about how there was a heavy downpour event that impacted, I don't know, the city of Des Moines, but Ames, was virtually unaffected. So there are techniques now that allow you to move the existing storms around different places where they could have happened, but they did not happen. So, and that provides a lot of interesting forcing data for analysis. For instance, you can take the June 30th, 2018 event that affected the city of Des Moines and move that stuff around throughout the Des Moines River watershed and see how that would have generated severe flooding throughout the watershed. So that's one aspect. And we've made a little bit of progress towards that. So in our team, there are people and students that have been working on this quite a bit. So the second point that I want to talk about is about climate models, global circulation models or regional circulation models. And you see that those models are getting to the point where they can make predictions. I haven't seen at the hourly data, perhaps I've missed that, but certainly at the daily data, they can make predictions about future weather going all the way to the 2100. So 100 years from now or 80 years from now. I would like to use those forcing data as well to improve and extend the analysis that I presented before. And lastly, another thing that is that I want to mention here, and that's I'm going to explain the reason why I said that I believe that I was being a little bit unfair to the cover crops, is because I feel very good. I'm fairly confident that the way we are representing how water moves, it is highly sophisticated. However, for the way we are representing the transpiration and the infiltration, I think we can do better. For instance, in the models, in all the simulations that I presented before, cover crops were always present from the end of October, and they were terminated in the first week of April, irrespective of previous weather or anything like that. So that happened every single year. The same happened for the row crop. For instance, the row crop agriculture disappeared from the model the first week of October. So, and for some years, perhaps that is a decent estimate, but for some other years it's not. So I don't have the flexibility, I guess, to account for the actual dynamics associated to the agronomic side. So, and I envision how coupling our hydrologic model with something like Upstream or any other crop growth model can be an improvement and can allow us to have the granularity, if you want, that is needed to account for the transpiration and infiltration and everything related to the land use. And with that, I think I'm gonna end here, Matt. Hopefully I didn't go over time, and that's all I have. Thank you.
No, perfect time. But we do have time for questions if anybody has a question or two. I think it's fascinating. I kind of ask a question or maybe comment, but fascinating the potential of kind of being able to move that storm around, or move around kind of an actual storm that's happened to see what that might mean for different communities and so forth, because really might help us understand, if we had one of those storms in a slightly different location, what it might have meant.
And there is a group that has made a lot of improvement towards having those data already processed, and it's from the University of Wisconsin. So Professor Daniel Wright, whom I haven't met, but they created a website that is called the Rainy Day for some of the students or people here who want to read more about that. I encourage you to Google the Rainy Day website, and they created already transposed storms. They allow you to select the area from which you want to take the storms, and they allow you to select the area where you want to apply the storms. Okay. So that's very interesting. And I'm working on a presentation that I'm hoping that I'm going to be able to put together for the Iowa Water Conference along the lines of the 2008 flood in Cedar Rapids. Could have been worse. And yeah, so I'm also very, very kind of interested in this topic.
There was a question, could you review again how much of the flow was estimated to be represented by tile drainage?
Yeah, so a lot of variation from one year to the other. The model, let me go back. So each one of the bars on the right-hand side represent how much of the annual flow in the entire domain came from tile based on the model predictions. And like I said before, so for a very dry year, that percent goes way up to 80%. But for a very dry year, we're not moving much water through the system. And conversely, like I said, for a very wet year, 2008, 2010, that percent goes way down to a little bit over 20 or 30%. But it might be moving way more volume of water through the tile than what actually was predicted by the 2012. So this is a percent of the total annual runoff.
And does the GHOST model have kind of, I guess, groundwater flow contributions then too?
It does. It does. It's a surface subsurface coupled model. So we do have the contribution. The model makes an estimation about how much water is moving from the ground surface domain to the stream, and actually the other way around as well. Yeah, okay. So losing the stream. So one of the many reasons why, and that's a little bit more on the numerics, one of the reasons why these models are computationally expensive, so take a little bit of time to run, is because they allow those fluxes back and forth. So once water gets into the river, depending on the topography and other conditions downstream, can get out of the river. So allow you, if you allow all those fluxes, that is numerically challenging, and that results in longer computing times. However, in my opinion, that results in a more accurate model as well.
Antonio, can you hear me?
Yep.
Yes, I can.
Yes. Okay. This is Malcolm. Hi. Thanks. A great presentation. I got lost a little bit, but in your penultimate slide, so I think it was slide 20. So where you had the 2080 cover crop scenario with the ponds, and you forward predicting with our future climate, was that correct? Was on that?
Yeah, it's a simple way. So I wouldn't call this a weather generation exercise. All I did was to alter the precipitation that was observed between 2002 and, yeah, exactly. But not every single data point, but just the heavy downpours.
Right. And so the NASA data you presented earlier said with high emissions, we're going to be looking at 20%. Is that correct?
Correct.
So really the way I'm looking at this, we're kind of still in a little bit of trouble, even with those putting in, am I seeing that right? Even with cover crops and about 20% natural vegetation and ponds, we still in a little bit of in a bit of a precarious situation. Is that correct?
Well, I mean, there are many ways to read this, right? So, I mean, I can argue against and in favor. So I can say, for instance, that let's say the MV 20%, CC 80% ponds, right? Yeah. You see that all the reductions for that particular scenario, which is the last column for each one of the index points, are positive.
Right.
So that is telling me that with that scenario in place and the heavy downpours delivering more volume, still you will see positive reductions with respect to the floods that we already saw in the 2002-2018 window.
Okay. Right.
So the negative reduction.
Yeah. And that's significantly enough. Okay, I got it. I was looking at it a little bit differently. Okay.
Yeah, I hear you. So that's what I said, that I have been kind of wrestling with how to present this best. I said it a couple of times, and that you are confirmation of that. So, but one thing to be said is that look at the blue bar, right? The blue bar is doing nothing, right? The blue bar is doing nothing and increased precipitation. So if anything below the blue bar, that's terrible. So even if it is a negative reduction, but it's not as severely negative as the blue bar, that is an improvement. Hopefully I'm making some sense.
Yes, no, got you. Okay. That's perfect, thank you.
There are two other questions that came in here. Is there a recommendation about a balanced approach to converting farmland, especially non-productive farmland?
Well, I don't have a kind of specific recommendation, but if for one of the things that I believe should be concluded from this study is that if for some reason a farmer decides to take some land out of production, excessive wetness, whatever, I think there should be a program to incentivize the planting of native vegetation, because it's something that was demonstrated with this analysis, the enormous flood reduction potential of that practice. Staying away from the floodplain is something that I didn't quite fully analyze for this particular study, but I've done it for other areas. And that appears to be also highly beneficial for the flood reduction perspective. And I would argue that perhaps from the economic perspective is beneficial as well, but I'm a hydrologist, I guess, so I don't get much into the economics, but I've seen numbers from the crop insurance program, planting on the, without the existence of that program, perhaps we wouldn't have too much planting on the floodplain.
Okay, the last one here, and it kind of relates to when you talked about the native vegetation. So thank you, very nice talk. What's the mechanisms represented in the model that it can explain the differences in the flood control capability between native vegetation and cover crops? Okay,
4 points. Excellent question, by the way. 4 points. Whoever asked that question is thinking like a hydrologist, so I like that person. So 4 mechanisms were altered to account for the effect of native vegetation and cover crops, by the way, as well. So transpiration was increased, infiltration capacity was increased, surface roughness was increased as well, and the water holding capacity was increased. In other words, water that was infiltrated was retained in the unsaturated zone as opposed to moving either to the tile drainage network or to the groundwater system. So those were the 4 mechanisms. So as you see, if you have some pumps, I guess, as I call them, taking water out of the system continuously, having the native vegetation that doesn't go away, that makes more room in the soil to infiltrate water and actually attenuate floods.
Okay. Excellent. I think those are all the questions, and we're right at about 4 o'clock. So if everybody can join me in thanking Dr. Arenas for an excellent presentation. It's a great contribution to the seminar series, and hopefully you can tell others that the webinar will be, or seminar will be archived on the Iowa Nutrient Research Center website, so people can go and watch that. And hopefully, I think you had your contact information up there, maybe on the one of the last slides. So folks have additional questions. Hopefully they can be in touch with you, Antonio.
Oh yeah, absolutely.
Thank you very much.
Okay, Matt. Thank you.